This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's problem is to evaluate at the origin the derivative of the function x gets mapped to sine of x cubed plus 6x. This can be done almost immediately by using basic rules of calculus. This is the first approach we will take. The derivative of f of x, denoted f prime of x, is equal to the derivative of sine is cos. Then to apply the chain rule, we first of all write the original function there. Then we multiply all of this by the derivative of the inside here. Differentiating x cubed is 3x squared. Differentiating 6x is simply 6. If x is equal to 0, then the derivative is obtained simply by replacing all x's with 0 in here. And we see that we have got 6 cos 0. Cos of 0 is 1, therefore the answer is 6. Despite being a very fundamental tool, calculus is not always taught in the best possible way. In particular, there will come a time when you want to apply differential calculus to nonlinear functions going from high-dimensional vector spaces into high-dimensional vector spaces. In that case, the traditional notation can sometimes lead to some complications. If interested, you can consult this article of mine. In terms of the bigger picture, three important things about the derivative are that it's the best linear approximation about a point. So calculus is about linear approximations. Now technically it's the difference that's linear. Because we might not be going through the origin, it's otherwise known as an affine approximation, although everyone says linear. Second point is that calculus only applies to some functions. If you forget this, then it seems magical in places. Out of all the functions in the world, very, very few are continuous and fewer still are differentiable, that is, are such that the rules of calculus apply. If the rules of calculus don't apply, then calculus itself is not very useful because we can't go very far. Perhaps one of the most useful properties of calculus is the chain rule, because it says that we can make a sequence of approximations and still get the right answer. We get the right answer at the end of the day. The rest of this video will elaborate on these 3 points. Particularly nice functions can be represented using a Taylor series, basically a polynomial that's infinitely long. For example, sine of x is equal to x minus x cubed on 3 factorial plus x to the 5th on 5 factorial and so forth. And so we see here that the coefficients are respectively 0 for the constant term, 1 for the x term, 0 for the x squared term, negative 1 on 3 factorial for the x cubed term, and so forth. You might well ask, why aren't there other powers here? Why only integer powers? And that comes back to only very special functions can be written in this form here. It's just that functions that are special are also very convenient and we tend to use them a lot. So this occurs very often in real mathematical work. Another example is that x plus a half x squared plus a third x cubed, etc. is equal to negative the natural logarithm of 1 minus x. If we know the Taylor series of sine x and know the Taylor series of negative logarithm of 1 minus x, one might ask, can we easily deduce the Taylor series of the composition negative log 1 minus sine of x? When we do this composition on the next page, we will see something that directly relates to taking derivatives. Here is my Taylor series for sine of x. Here is my Taylor series for negative logarithm of 1 minus x, which I abbreviate to g of x. And we want to compute the Taylor series of the composition g of sine of x. And we essentially do this just by simple substitution. So g of sine of x is g of, and we replace sine of x with its Taylor series in here. And then we apply the Taylor series. So g of something is equal to that something, just the x, which is the term in green, so whatever is in here gets copied down here, plus 1/2 times the argument squared. So down here in yellow, I've got plus 1/2, and then in brackets is my argument, which in this case is the Taylor series for sine of x, all squared. Then for the third term, we've got the argument cubed divided by 3. So I've got 1/3 the argument, which is the Taylor series of sine of x, all cubed, and so forth. On the next page, we compute the squared term and the cubed term, and the important thing is to keep an eye on what powers of x can appear. In particular, in this term in red here, which we've omitted, which involves the argument to the power of 4, because my argument contains x and x cubed, etc., when I raise it to the power of 4, the smallest power I'll get is x to the power of 4. So if we are only interested in determining this up to powers of 3, then we can omit the fourth term. This will make more sense presently. To compute the squared term, we can do it from first principles, write the square explicitly as the product of the Taylor series here times itself, and then when we try to compute a product of two things in brackets, we know that we look at each element pairwise and we expand each of the products that way. So in particular, the first thing we have is x times x to give me x squared here, denoted by the purple correspondence. Then the next one we can do is the first term in the first bracket and the second term in the second bracket. Pairing these together, x times negative x cubed on 3 factorial gives me negative x to the fourth on 3 factorial. Then we can take the second term of the first bracket with the first term of the second bracket as denoted by this blue line here, and again we get x times x cubed on 3 factorial with a negative here to get negative x to the fourth on 3 factorial. And then all other powers, any other pairing here, whether I pair the first term here with the third term here, that will be x times x to the fifth, gives me x to the sixth, or I pair the third term here with the first term here, that would also give me x to the sixth, or I pair the second term with the second term, that will also give me x to the sixth. So everything out here contains powers of x to the sixth or higher. That's a key point. Finally, we can simplify this. I've got two terms with x to the fourth, so I can collect them. So this Taylor series, when squared, gives me x squared minus 2x to the fourth on 3 factorial plus terms that involve powers of x to the sixth or higher. We can do the same thing to compute this Taylor series to the power of 3. If you like, you can write this out 3 times, and then we have to take, to compute the product, we have to form every possible pairing, one term from the first bracket, one term from the second bracket, one term from the third bracket. We form every possible pairing, multiply them out, and we end up with an expression like this. The same thing happens as up here. We find that we can compute the lower order terms here, and everything left we know is going to involve, in this particular case, powers of x to the sixth or higher. To both summarize what we have done so far and to complete the calculation, we wanted to compute the Taylor series of g of sine of x, given the Taylor series for sine of x and of g of x. Inside each of the brackets is the Taylor series for sine of x, because that forms the argument to g of x, and then outside the brackets we essentially have the Taylor series for g. Next, we evaluated this Taylor series to the power of 2 and the same Taylor series to the power of 3, and we're allowed to neglect higher order terms. By doing that, we arrived at this expression here, and because I've chosen to truncate the Taylor series of g at the power of 3 here, I don't have the power of 4 term here, then this expression here is only accurate up to powers of 3. terms of x to the 4 and higher, some of these terms might be missing in here. All that remains then is to group like terms together. So in terms of x, it only appears in the first term here. So x comes down here. X squared term, this is the only x squared term, so we have a half x squared. For my x cubed term, I've got a contribution here and a contribution here, so putting them together, I end up with 1/6 x to the cubed. Although I've included some higher order terms in the brackets here, because I'm omitting an x to the 4 term out here, my final answer is only accurate up to the x cubed term here. Crucially though, provided these individual terms here are accurate up to powers of x to the 3, then the full expression will also be accurate up to the powers of x to the 3. We can check the Taylor series we obtained is correct. Here I am asking Wolfram alpha what the Taylor series of negative natural logarithm of 1 minus sine x is, and it gives me the answer down here, and we see that we computed correctly the first 3 terms. How does all this relate to differential calculus? Well, the first observation is that a Taylor series gives us an approximation about the origin of our function. For example, sine of x is equal to x minus x cubed on 3 factorial plus x to the 5th on 5 factorial, etc. Consider what happens when x is very close to 0. The x cubed term is going to be even smaller. If x is 10 to the minus 3, then x cubed is going to be 10 to the minus 9, for example. So we claim that we can ignore higher order terms and approximate a function by the first few terms in its Taylor series, and this should be accurate about the origin, close to when the argument is 0. A simple test, I can choose my argument x to be 0, then 0.05, 0.1, 0.2. I can evaluate sine of x, the function I care about, to get these values here. Remember to set your calculator to radians when you do this. And I can also evaluate my Taylor series approximation. In this case, I'm just going to keep the first term x here, because that corresponds to what differential calculus is going to do. So I discard all the higher order terms, and I'm approximating sine of x with simply x. So I've written x here again. And we can compare. At the origin, it's perfect, and indeed, it's an approximation about the origin, so it should be exact at the origin. If I'm a small distance from the origin, then my approximation is correct to at least 4 decimal places. Going to 0.1, I'm still very close, and at 0.2, I'm still very close. And that's simply because my higher order terms involve x to the power of 3 and higher, and 0.2 to the power of 3 is a relatively small number still. Hence we get a good approximation to sine of x just by keeping the first term here. We can think of differential calculus as a somewhat mild generalisation of approximating functions by first order Taylor series. Technically it's a generalisation because there are some functions that we can differentiate but that don't have a Taylor series expansion, but nevertheless this Taylor series perspective captures all the intuition we need to understand differential calculus. Previously we just looked at a Taylor series about the origin, but we can look at a Taylor series about any point x simply by writing our function as f of x plus h, where x is the point where we care about and h is a small perturbation, a small number left to right of x, so to speak. A basic theorem of Taylor series says that if f of x has a Taylor series about x, then its coefficients can be found by looking at f and its derivatives. The constant term is just f of x. The next term is the constant is the derivative of f evaluated at the point of interest multiplied by h. The next highest term involves the second order derivative of f, and so forth. While it's very common to just think of the derivative itself and say that it's linear, we have to keep track of the point about which we're making the approximation, and hence in many ways it's better to think of a derivative as an affine approximation or as a first order Taylor series approximation to the function we care about. Next, we will look at two examples to see how this works in practice. Recall today's problem. We were asked to find the derivative of this function at the origin. We did it originally using basic rules of differential calculus. We will do it again by taking a Taylor series approach. This Taylor series approach provides some good intuition, even if it's not always the fastest way of solving problems. Often for more complicated problems, it is always a trusted method that you can use if ever you find that the rules are a bit confusing to apply. And if you refer back to the article that I wrote, that can indeed be the case sometimes. Essentially, we just want to find the first order Taylor series expansion of f of x about the origin. So we want to write f of 0 plus h is equal to some constant plus some other constant times h plus higher order terms. Once we've done this, we know that this term right here will be the derivative that we care about. All we do is substitute 0 plus h into our function here. So we get f of 0 plus h is equal to sine of 0 plus h cubed plus 6 0 plus h. The trick is we only care about constant terms and terms involving h. Any higher order terms of h we can replace with plus dot dot dot. This means we can write this as sine of the h cubed term is a higher order term we can ignore, so we just have sine of 6h plus dot dot dot. When doing this for the first time, it's probably better to explicitly write this as 0 plus 6h plus dot dot dot. So we are keeping the first two terms of the Taylor series. Next, we need to know the first order Taylor series of sine, and we want to know it about the origin because the constant term is 0. Because we want the Taylor series about the origin, we in fact already know what it is. We know that sine of theta is equal to theta minus theta cubed on 3 factorial plus higher order terms, and in fact we only want the first order Taylor series, which is just theta plus dot dot dot. Therefore, we conclude that this is equal to 6h plus dot dot dot, or for pedagogic purposes, 0 plus 6h plus higher order terms. This tells us that our function f of x at the origin is equal to 0, and its first order derivative at the origin is 6, and more importantly, it tells us that we can approximate this function by 6x about the origin at 0. For reasons that will become clear on the next page, I've replaced x with 0 plus h, so this answers in terms of h, but indeed we can think of f of x is approximately equal to 6x when x is very small. Our second example involves the same function, but now we want to know the derivative at x equal to 1, or equivalently the Taylor series about x equals to 1. Therefore, we want to write f of 1 plus h equals, substituting 1 plus h in, we find that that is sine of 1 plus h cubed plus 6 1 plus h. Next, we expand the inside and we remember that we only care about constant terms and terms with h. We don't care about higher order terms. Therefore, 1 plus h all cubed, we care about the constant term, we care about the h term, but we don't care about the h squared and h cubed terms. Similarly, for this next term here, we care about the constant term, we care about the h term, we don't care about any higher order terms, even though there aren't any for the second term here. Simplifying, we get that that is sine of 7 plus 9h plus higher order terms. Now we see we need the Taylor series of sine, not about the origin, but about the number 7. Trying to use our Taylor series about the origin, in this case, is not going to help. We need a faster way of trying to find the Taylor series of sine of x about x equals to 7. We can do this by actually remembering the formula for a Taylor series in terms of the derivative. The Taylor series of a function at x perturbed by h is equal to, the constant term is f of x, the first order term, the constant, is the derivative of f at x times h plus higher order terms. So therefore, for sine of 7 plus a small perturbation theta, we have that that's equal to sine of 7. That makes sense because when theta equals to 0, we have indeed sine of 7 here, and when theta is 0, all these other terms are 0 because they contain theta or higher powers of theta. Then the linear term here, well, the derivative is the best linear approximation. Because the derivative of sine theta is cos theta, that's just a rule we learn in calculus, we see that the first order term here must be the derivative of sine evaluated at 7, in other words, cos of 7 times theta. Continuing from before then, we therefore get that f of 1 plus h is equal to sine of this, and that is equal to, from this equation here, sine of 7 plus, and now my theta is just 9h, so I've got cos 7 times 9h plus higher order terms. The conclusion is that the derivative of f of x at x equals to 1 is 9 times cos 7. More importantly though, our best linear approximation of our function about x equals to 1 is sine of 7 plus 9 times cos 7 times h. Indeed, we only really care about the derivative because we care about first order approximations. Finally, we look at some basic rules of differential calculus and how we can derive them, at least intuitively, from a Taylor series approach. The first one is that the derivative of x to the power of n is nx to the n minus 1. To see this, at least in the special case when n is a positive integer, we can do our Taylor series expansion. So f of x plus h is equal to, substitute x plus h into our function, we get x plus h to the power of n. Think of this as x plus h times x plus h n times. Then to expand this out, well, the first term will be x times x times x times x. We get our x to the n here. Our next term will consist of choosing x from all but one of these terms and h from one of these terms. And there's n ways of doing that. So we get x to the n plus nx to the n minus 1 times h plus, and every other term here will involve 2 or more h's. This also follows immediately from the binomial theorem, if you know what that is. As a concrete example, if we want to differentiate x to the cubed, we get 3x squared. Another rule is that if one function is a constant times another function, then the derivative of that function is just the same constant times the derivative of the function here. If we think in terms of linear approximations, this should be quite obvious, and it follows immediately from the following Taylor series expansion. F of x plus h is equal to f of x plus the derivative of f at x times h plus higher order terms. So g of x plus h is just alpha times this Taylor series expansion here. So alpha times f of x plus alpha times f prime x at h. And the constant in front of h is simply the derivative, thus proving this result here. As a specific example, if we want to differentiate 6 of x, Well, first we ask what the derivative of x is. Well, x is just x to the power of 1. So from the page before, its derivative is 1x to the power of 0, or in other words, just the constant 1. And so the derivative of 6 of x is just 6 times that. In other words, it's 6. Another basic rule is that to differentiate the sum of two functions, we just have to differentiate the functions individually and then add them together to get the derivative. Hopefully this is becoming familiar. f1 of x has got this as a linear approximation, f2 of x has got this as a linear approximation. We simply add the two together, and so we find that the constant term is f1 of x plus f2 of x, and the linear term in h is just f1 prime x plus f2 prime x, showing that the derivative is f1 prime x plus f2 prime x. As an example, if I want to differentiate x cubed plus 6x, then I first differentiate x cubed, which we did before to get 3x squared. Next I differentiate 6x to get 6, which we did before, and then I simply add them to get the derivative of the whole expression here. The last rule we will look at is the chain rule. If g of x is the composition of two functions, then its derivative is given by this formula here. We differentiate the first function f1 and we evaluate it at f2 of x, and then we multiply the result here by the derivative of the inner function f2 evaluated at x. To see this, we evaluate g at x plus h in a first order Taylor series, substitute x plus h into the expression here, so we get f1 of f2 of x plus h. We keep f1 for the moment, we expand f2 in a first order Taylor series, so we get f2 of x plus the derivative of f2 at x times h plus higher order terms. The trick to seeing what's happening, let me call this term x tilde and let me call this perturbation h tilde. So in effect I've got f1 at x tilde plus h tilde. Applying my Taylor series for f1, I get about x tilde. I get f1 at x tilde plus the derivative of f1 at x tilde times the perturbation h tilde. And now all I do is I replace x tilde with f2 of x, and I replace h tilde with f2 prime x times h to get this expression here. And the term in front of my h is the derivative here, so we've proven the result. The way we apply this in practice then, for example, the problem of today was to find the derivative of sine of x cubed plus 6x. So to do this, based on this formula here, first I write down the derivative of my sine, which is cosine. That's one rule I won't cover here, but that's true. The derivative of sine is cos, so I've got cos evaluated at the inside function, so that's evaluated at x cubed plus 6x, multiplied by the derivative of my inside function, which, as we saw before, was 3x squared plus 6. This gives us the full derivative of the function that we were given today, and of course the problem was to evaluate this at x equals to 0, and we end up with the same solution as we did at the start of this presentation.